All right, here we are again. Man, it's been a long layoff, hasn't it? It seems like years since we met last, but all right, no, here we are. So we've got some important things to do today. We have a second sample midterm to deal with. So this is, of course, based entirely on chapters 6 and 7. And the actual midterm, of course, will also be 6 and 7. The first one, you should have it ready by no later than midnight tonight, along with chapter 6 and 7 problem sets. And then I think we decided that this one would be due on the 18th, maybe. Does that sound right? Let's go look at Moodle for a second. I know that I have an announcement in there. Let's see. What did we say about that? Due dates. This must be it. Okay. Oh, here we go. This just says that tonight at midnight, you're supposed to have the first midterm ready and the chapter 6 and 7 problem sets. And I've received many of them already. But what about the second midterm? Ooh, I guess we didn't get that one in there. No. All right. So I think I'm pretty confident. I remember saying that you could have a week to do this one because, of course, you know that this is the last full week of the semester. So today's the 11th. Let's pick one of these cool calendars. And so, yeah, all right, that sounds right, because the last official day is the 19th. So during the week of the 18th, what we'll have to be doing is reviewing for the final, which is on the remaining chapters 8, 9, and 10. So let's just agree that you should have the second midterm, due by the 18th. And by that time, there will also be more problem sets. Wow, this is piling up, isn't it? So, all right, let me throw an announcement in here. So how about this? This sounds about right. The second midterm and chapter 8, 9, and 10 problem sets will be due on midnight or at midnight on Monday, January 18th, 21. Okay, and then we'll pick a date for the final. Now, again, I may have some flexibility there because our last official day is a Tuesday. It's very possible that I can give you until the following Monday, but I'm not positive if I do anything. So I'll have to check out with the school. The last thing in the world we want is to get the grades in late. So I'll find out exactly how much time I can give you, but I'm positive you can have a minimum until that Friday, let's say, but we'll see what we can do. So for these, though, we really should have everything done by Monday because, like I said, I mean, that's the last day of school. So we can't go past that. All right, so that's that. So in the meantime, let's just get to it. We have our sample midterm waiting for us. And so here's all the key terms that we've learned. And you know them very well, I hope. And then here is our selection of short fill-in answers. And so let's get started. All right. Well, first of all, what exactly is a discrete random variable? Now, obviously, because these answers are in English, there's a lot of ways you can explain this. But basically, what you should mention, there's a couple of key ideas that you have to mention here. A discrete random variable assigns numerical values to the outcomes of a random experiment in which there are only a finite number of possible outcomes. So you're basically explaining two things at once here. The idea of the random variable is that it assigns numbers to the outcomes of that random experiment. The discrete part refers to the fact that there's only a finite number of possibilities. So let's say you're flipping a coin and heads are what you're interested in. The random variable will assign to each outcome the number of heads. Okay, but the number of heads sets a limit on, the number of flips sets a limit on how many heads you can have. So if you flip a coin 10 times, you clearly can't have more than 10 heads. And because the number of heads has to be an integer, that means that there's only 11 possible outcomes, and anywhere from 0 to 10 heads, which means 11 total possibilities. And of course, 11 is a finite number, and therefore that random variable that assigns heads, numbers to the heads, is going to be discrete. All right, so then continuous is the same principle, except that we have an infinite number of possible outcomes. So I'm going to take advantage of that, and I'm going to make one tiny change here. Okay, so a continuous random variable now also assigns numbers to the outcomes of a random experiment, except now there are an infinite number of possible outcomes. Okay, like the time until the next phone call, for example. That's infinite because it can have a fractional component. In principle, the number of different times that can occur between now and the next phone call is infinite. All right, very good. Now, which probability distribution is based on a series of independent trials? That would be the binomial distribution. If you're not sure, you can go through your slides. It's definitely mentioned in there. Now, here's a tricky question. For which probability distribution are the expected value and the variance equal? So what is that all about? Well, let's go back to chapter 6 for a second, just so you can see what this question is all about. All right. So we're going to look at chapter 6, which is our discussion about discrete probability distributions. And of course, if you recall, we looked at two different examples, binomial and Poisson. All right, so with the binomial distribution, if you look at the moments, you'll see that you have, let's find that, hold on. There it is. Expected value is n times pi, variance is n times pi times 1 minus pi, standard deviation is square root n pi 1 minus pi. So that's clearly wrong because it says which one has the same expected value and variance. Okay, so let's jump ahead to the Poisson, and you'll see, oh, wait a minute. Look at that. The expected value and the variance are both equal to lambda. So the correct answer must be the Poisson distribution because the expected value and the variance are equal to each other, which is extremely unusual. In fact, as far as I know, it's the only distribution in which this is true. Although you never know, there's a lot of very bizarre distributions floating around out there. We've only learned the two most important ones. Now here it says, what are the two values that uniquely characterize the normal distribution? Okay, that would be the mean and the standard deviation. So remember, we drew those graphs which showed how they're different from each other. The only thing that really separates two different normal distributions are the mean and the standard deviation. Okay, so that's what we're looking for here. If you know those two values, that you know everything you need to know about that probability distribution. It's kind of like for an individual, if you know their social security number, that's plenty to identify them as that unique individual. So here, it's the mean and the standard deviation. All right, now the standard normal distribution, as you recall, is uniquely characterized by the idea that the expected value is 0 and the standard deviation is 1. So if the standard deviation is 1, it must be the case that the variance is also 1. All right, that's the reason it's 1, because the variance, the standard deviation is 1, which means the variance must also be 1. Now, what probability distribution can be approximated with the normal? That would be the binomial. We've already seen, we did a couple of intense examples about this. There's actually other cases too, but this is the only one that we actually covered. All right. So we know that the binomial distribution can be approximated with the normal distribution, which saves time if we have a lot of outcomes. Let's say, for example, we want to know the probability that when we flip a coin 100 times, we get anywhere from 50 to 60 heads. The options we have are to calculate all the individual probabilities from the binomial distribution, or just do it once with the normal. Okay, now as we just saw when I scrolled by, the variance of the binomial random variable is the square root, not the square root, it's just plain n. Oh, so I don't need this. It's n times pi here we go, and then 1 minus pi. And again, if you forget, you can just go look it up in the slides. It's there in a very convenient spot, listed under moments. In fact, you know what you can actually do with these slides? Suppose you come in here and say, oh, for God's sakes, I don't know where it is. Look at how easy that is. And you're done. Look at that. How easy is that? Okay. So don't forget, it's so easy to find things with these slides. Now, what does lambda represent? Okay, so remember, lambda is the thing that characterizes the Poisson distribution. So what you can do is describe it as the average number of events that occur during a given time interval. That information has to be provided to you in the problem, but that's what it actually means. So if you're told that lambda equals 3, that means something happens on average, let's say 3 times an hour. And that's what the Poisson distribution is based on. Okay, now this one, we have to be careful. We have to make sure we understand what this question is actually asking. What formula is used to transform a normal random variable into a standard normal random variable? Okay, so in case it's not crystal clear what that means, that will be this formula. By the way, if you find a question on any of these tests or homeworks that you're not sure about, all you have to do is send me an email and I'll clarify it for you. This is not meant to be a interpret my questions class. This is a stats class. Okay, so if you don't understand what I'm saying, just ask me and I'll clear it up for you. All right, so in other words, I'm asking you for this formula. Remember, we use this multiple times to convert a normal random variable, like the rainfall, for example, into a standard normal version so that we can use the tables if we choose to do so. If we don't use the tables, this isn't really necessary, but it's good to know what's actually happening here. This way, it's easier to understand what is actually going on when you calculate probabilities for X. All right, now it's time for our calculations. This is where the fun begins. So we've got some probability distribution here. Now, this is not binomial. It is not Poisson. It is a probability distribution that, and in principle, you can have any number of probability distributions. They don't have to necessarily fall into a major category like binomial or Poisson. All right, there's many others that don't have their own names. So here, for example, they want to know, is it valid or not? So then you have to ask yourself, what does it mean for a distribution to be valid? So you might say then, well, I don't remember. When did we talk about this? All right, well, let's find out. Here we go. This is what it takes to be a valid distribution. Each individual probability is non-negative. Now, what we could actually typically do here, you can explain it in the following terms. Let's agree that this is probably the best way to go. Each probability, yes, because each probability is between 0 and 1, and the sum of all the probabilities is 1. That's probably the best way to explain it. There's so many other ways you could do this. I like that the best because it's compact and it tells us everything we need to know. So in other words, they have to add up to 1, but individually they must be somewhere between 0 and 1. If they're not, then they violate 2 of the key axioms of probability. Is X discrete or continuous? Okay, well, X is discrete because it can only attain three possible values, and 3 is a finite number. Okay, notice it only has 3 possible values, which means since 3 is finite, that implies that it must be discrete. Okay, and by the way, here's a helpful hint too. If it was continuous, it would not be possible to have a chart. A chart of a continuous random variable would have an infinite number of rows, and so obviously we can't have that. So just the mere fact that it's in a table tells you that it's discrete. Okay, that's the practical solution. All right, now we have to do some actual math here. Expected value. Now, this distribution is not Poisson, and it is not binomial. We cannot, therefore, take advantage of those special shortcut formulas. We have to do all the work ourselves. Yes, I know, it's a nuisance, but we have to do it. So remember this formula. Xi, we're going to take all the x's in our chart and multiply each one by its probability. Then we'll add them up, and the result is our expected value. Now, where did we see that formula? That's in chapter 6, or whoop, that's 9. Okay, where's 6? Somewhere in here. There we go, right there. Okay, so the expected value is EX. We simply multiply all the x's by their probabilities. Now, in this chart that we have in the test, these are the x's and these are the probabilities. In fact, you know what I'm going to do? Let me copy this down here. And then I'm going to put these little notations in here. This is x1. Okay. Okay, it's time to do something about the options here. The thing is, if you use Word a lot, you'll notice that it has a way of butting in its opinion where it's not wanted. Okay, I usually just turn them all off because it doesn't always know what it's doing. Like here, for example, I want a lowercase x and it's refusing to let me have it. So that means you just turn off the options. You know what? I know how to spell. I'm okay. I'll make these decisions for myself, please. But by default, it assumes that you don't know anything and it tries to correct everything. And that's good if you really can't type or if you can't spell or if you're, let's say English is not your first language. But if not, then you want the option of doing it yourself, So that's what I choose. All right, now over here we have the probability of x1. Probability. This way you can see what's going on with this formula. Now, you don't have to do this, of course. I just want you to see very quickly and easily what exactly is going on with this formula. So that when what just happened there? Man, this thing is really pushy. It's trying to push its opinions on me as to what I should be doing. All right, so here we go. So the expected value then means we're going to multiply each of these x's by its own probability. We'll go through it row by row. Okay, now just to avoid mistakes, you might want to think about calculating each one separately before you combine them. You want to, not every single step is absolutely necessary, but you want to be careful too. So I think it's a good idea to write these all out separately and then add them up. And so you've got an expected value of 280. which means on average, X has a value of 280. Now, here's a helpful hint. If you get this part wrong, then B and C have to be wrong. So you want to be extra careful with something like this. Okay, so there's D. Compute the variance. Now, what formula do we use for variance? Now, again, this is not the binomial or the Poisson distribution. You must use the general formula, which is this one. So I'm just going to copy this right in here. And you can see this formula requires knowledge of this 280 that we just found out. So again, if you got that wrong, you're going to have a problem. All right, what exactly in English are we being told to do here? You take each X one at a time. You subtract off this expected value that we found up here. You square the difference, and then you multiply by that probability. The probability in this first case that X equals 100 is 0.30. Okay, then we go to the next row, 300 minus 280 squared times 0.50. And then finally, 500 minus 280 squared, okay, times 0.20. Now, again, I would recommend, what you might want to do here, for example, and again, this is just to hopefully avoid making mistakes, because you can see with a formula like this, it would be super easy to make mistakes. I think the way to minimize mistakes is to avoid skipping too many steps. Okay, so I'm going to calculate the differences. All right. Now what? Well, why don't we square them? Okay, that should come next. Okay, so negative 180 squared is 32,400. 20 squared should be 400, sorry, 400. And then finally we have 220 squared, 48,400. And then we multiply that by oh, something went wrong here. What happened? This, I don't know what I did here. This is 0.20. All right, so already I noticed, see, because I wrote it out step by step, I noticed this mistake. I made a typo here. That should have been 0.20, and I accidentally made it 0.50. So again, I think that writing everything out step by step makes it easier to spot your mistakes before you make them, okay? So that way, this last one is 0.20. Now, you should multiply them out separately and add them up. So the first one, for example, is 9720. The second one is 200. And the third one is 9680. And when you add those up, you get 19,600. Okay, so that's your variance. What about the standard deviation? Well, that's easy, because as you know, all we have to do then is take the square root of the variance, which we've just gotten through calculating. So, okay, that's enough. That's enough. You see what I mean? It's like constantly trying to boss you around. All right, so there's our square root. Okay, so what I'm going to do is take the square root of 19,600. Eventually, when the equation editor wakes up, here we go. Now, here's a big surprise for you. It turns out that this is actually an integer. It's 140. Well, that doesn't usually work out so nicely, does it? No. Okay, so the standard deviation is 140, and you're done. There you go. Very good. All right. Now, the next question is kind of interesting. And it'll help determine if you're able, you should ideally be able to identify what kind of problems each one of these are. So number 2 tells us the following. We have a special M&M Mars bag of M&Ms, which is designed to be brought out at Easter time, clearly. And it's set up to have 40% purples and 60% pinks. Now, you might not think that M&M's makes those colors, but yes, they do. In fact, if we ever are allowed to go into Manhattan again, which you might want to investigate, there actually, believe it or not, in Midtown Manhattan, in the Times Square district, is an entire store, and all they have is M&Ms and M&M merchandise. You have to check this place out. You must. Okay, well, maybe it's not open now, but this is what it actually looks like. And if you go inside, there's nothing in there. Now, what they've got here, well, that's the London store, but it's the same. Literally every color that they make is in these enormous tubes that go all the way up to the ceiling. And you can buy, they give you a bag, and you can buy whatever combination of colors you want. You just have to watch it, because you might think that your bag isn't that heavy, but you might buy a bunch of colors and get to the cash register and suddenly discover you just spent $40 on M&Ms. So you have to be careful, but you can have every color and look at them all. Who knew that they made all these colors? It's unbelievable, the colors that they have in there. There's something like 23 different colors, of which maybe 5 or 6 of them are normally available in a standard bag of M&Ms. So the rest of them are very unusual, and you're not going to see them unless you go to the store. So yes, they do have purple and pink, and yes, they have special selections that you can buy. It is. Oh, I did not know that. How do you like that? So that's where they make these guys. Okay. Interesting. Yeah, I've been to the store in Midtown Manhattan. I didn't know that their factory was in Jersey. Okay.
Yeah, the security is tighter than the FBI. It's crazy. If you
I'm sure it is. Oh yeah. Are you kidding? The value of their brands and trademarks is beyond belief.
they like take
That's why.
license plate. They like take pictures of you when you go in there. It's like this whole thing.
Wow.
Yeah.
Well, that's good to know. Okay. So yeah, because it's all trade secrets. They can't let their competitors steal their secrets. But yes, you can have anything you want. So, and they have customized ones too. You can actually have your name printed on them, all kinds of stuff. But anyway, here's the key though. It's telling you that we're going to define success as a purple M&M. Now, success tells you right off the bat that this must be the binomial distribution, because each M&M is either purple or it is pink. If I pick up an M&M out of a bag, I'm conducting a trial of an experiment where each outcome is either pink or purple. Now, assuming the bag is large enough, the colors should be independent. In other words, there should be enough M&Ms when I choose these colors that as I keep picking them, I'm not influencing the total proportion of purples and pinks. So by picking these out of this bag, I'm conducting a binomial experiment where there are only 4 trials, because I'm only picking 4 of them. So we know right off the bat from just reading this thing that, first of all, this is a binomial experiment. Each outcome is either success, which means purple in this case, or failure. And it tells you right in the problem that pink is the failure, purple, it honestly doesn't matter which is which, as long as you're consistent. But let's just be consistent. Let's all choose purple as success. There are 4 trials of this experiment. In other words, we pick 4 M&Ms, and each choice is a trial. And the colors are, of course, well, I shouldn't say the colors, the trials are independent of each other. Okay, therefore, we can use the binomial distribution to compute these probabilities. Okay, so that's the bottom line. If you misunderstood what they were telling you, you're not going to get it right. Okay, now we're going to be asked to calculate the probability of no purple M&Ms. So we got 2 options here. We can use the formula that we learned in the slides. Let's go grab that formula here. Okay, now this means, of course, we have to fill in all the numbers ourselves. And also remember this formula here, nx, let's recall what that means. There it is. So what you can do is rewrite this as the ratio of n factorial, over x times n minus x factorial. That might be the best thing to do. And then just plug everything in. So keep in mind that n equals 4 and pi. Oh, yeah, that's the other thing too. It tells you here that 40% of the M&Ms are purple. Pi represents the probability of success. Therefore, it must be the case that pi is 0.40. Okay, so remember, we're calling purple a success, and we're assuming that 40% of the M&Ms are purple. All right, now, when in the first case, we're being asked to calculate the probability that x equals 0. So this lowercase x in the formula is 0. All right. Oh my God, what's going on here? 0, 4, 0 again. Wait, sorry, that's 0. So this is 0.4. And the exponent is 0, or x. And then here we'll have, let's replace this with 0.6. And then the n minus x, will replace that with 4. And 4 minus 0, or 4. Okay. Okay, that's good. All right, so we plugged in all the numbers. So now what you need to do is calculate each term separately. The first one, if you throw that into your calculator, what you'll see is that, actually, let me do this real fast. Might be quicker to handwrite it. So this clearly is just 4 factorial, and you can see that these actually cancel each other out. And 0 factorial equals 1. Or rather than canceling it out, why don't we do this? Why don't we just write in the actual numbers? This is 24 over 1 times 24. And that just equals 1. Okay, so that's easy. So this expression equals 1. Now, 0.40 raised to the 0 power is also equal to 1. So we got 2 1s in here, so that makes things a lot easier, doesn't it? Yes, it does. The tricky one, of course, then is 0.6 raised to the 4th power. So go to your calculator and you'll discover that it is 0.1296. So the entire probability is 1296. Okay. Beautiful. So we'll do let's do this. Now if you happen to have the Texas Instruments calculator, this can be obtained as follows. Okay, if you have it, you probably should use it. If you don't, then that's okay, because you know how to do it the traditional way. So what you're looking for is second VARS, choose binom, make sure it's PDF, okay, not CDF. Okay, so if you look in that menu, you'll see that it's about, on mine, it is A. So then you need to provide it with 4 pieces of information: trials, which is N, and we have 4. It needs to know P, the probability of success, and it needs to know X. It's called X value, which is 0 in this case. So you choose to let it run, you calculate it. So remember, it's 4.40 and 0. And that should give you the same thing. It does. All right. Excellent. How about part B? What exactly is part B? So part B asks us for the probability of getting 1 success, or 1 purple. So what changes this time? All right, let's scroll back up there. 1 purple. So now I'm just going to copy some of this stuff. And we'll do it again with X equals 1. Okay, so this hasn't changed, and these will never change within the same problem. Okay, there's the formula. This is the meaning of what we're doing. So what I'm going to do here is change the x's from 0 to 1. Okay. So we have 1, 1, 1, 1. But that means that now this one is n minus x, so that becomes 3 now. Okay, so just be aware of that. All right, now this piece becomes this. Okay, so this is now 4. 0.40 to the first power is 0.40. So our calculations will be pretty straightforward. We'll have 4 rather, times 0.40. Now, 0.6 raised to the third power is 0.216. Okay, so what are we going to wind up with? Is, let's see, 0.3456. So when it comes to probabilities, it's pretty standard to round it to 4 places, but unless it's a very small number, then you can round it a little more. I mean, illustrate it with more places. In other words, this is not a tiny number, so we'll use 4 decimals to represent it. Up here, we ended up with 1296. Okay, and of course here too. Now, once again, we may have the Texas Instruments calculator, which means We can do it like this, except we have to make one tiny little change right here. X is 1. So if you run through that one again, you'll get the same thing. 3456. What do you know? All right. Now for part C, choosing a trick question, at least one. Well, it's not really a trick question, but there is a quick way of doing this. So basically, this is the same as this. That's a lot of calculations. I think you'll agree. If we can find a shortcut, that would be fantastic. So here's what we're going to do. We're going to make the following claim. Suppose I went through all the possibilities. One of these must occur with certainty, so therefore the sum of those probabilities must be 1. So algebraically, what if I did the following? What if I subtract x equals 0 from both sides? Oh, wait a minute. That means instead of doing all this work, all I have to do is this. And so my answer, since we already know the probability that x equals 0, man, that's already been taken care of for us. The probability of at least 1 is 1 minus the probability of getting none. I think logically that makes sense. And 0, remember, was 1296. Wow. Now this is a shortcut. Look at how much work we just saved. And so 1 minus 0.1296 is 0.8704. Wow, that was a nice time saver. If you didn't already calculate the probability that x equals 0, you would do it right now and then plug it into this formula. And I'm sure you'll agree that that's a lot quicker than actually doing it directly by doing all of these. That would take a long time, which we don't want to do. And it also introduces the chance of making mistakes. Okay, now there's more. We have to calculate the moments now. The last 3 questions involve the moments. But remember, this is the binomial distribution, so we can get away with using the shortcut formulas. Okay, well, that's kind of nice. For example, sorry about that. Expected values we saw earlier is n times pi, which in this case is 4 times 0.4, which is simply 1.6. All right. So what that means then is that if we keep repeating this experiment over and over and over again, on average, we should expect to get 1.6 purples when we draw 4 M&Ms out of the bag. Or even cooler, take it from one of those huge cylinders that goes all the way up to the ceiling, but then they're not mixed together. So, but they do sell previously created packages for you. Like, for example, they have an Easter set, they have a Thanksgiving set, they have a Christmas set, they have a Yankees set, they have a Mets set, they have everything. Okay, the store's got 5 stories to it. You wouldn't think that there would be that much need for that much space, but it's just unbelievable. All that merchandise, it's like anything that you possibly could buy, you can get it in an M&M's format in that store. Like, I don't know, if you wanted to buy a beach towel, well, there you go. They've got it with M&M's all over it. Oh yes, they have everything. Okay. That's why they need five. And that's why also, until the COVID came along, it never closed. That store was always open because they needed to be. There were people in there round the clock. You can probably guess that right up the street is the Hershey's store. Same thing, except maybe not quite as cool, but it's the same principle. All right, anyway, so the variance, I went back and I grabbed the formula for variance. And I've got 4 times 0.4 times 0.6, which gives me a variance of 0.96. Okay. And then, of course, the standard deviation is literally just the square root of that. Okay, so let's try that. All right, I'll do it by hand. That's okay. No, here it is. Okay. So we've got the square root n pi 1 minus pi. Okay, and so we plug in the numbers. 4.4.6. Okay, so if you take the square root of that, that's approximately equal to 0.98, let's say. Okay, so that's that. And you're done. Very good. All right, now we're ready for number 3. Now, number 3 is very similar to number 2. We're going to make an assumption here. We're saying that 10% of old people are left-handed. Now, basically, now you know that in the real world, some people are ambidextrous. They're kind of lefty and righty, and they can do both. But let's just assume for the sake of this problem that you're either one or the other. You're 10% of all people are lefties, 90% are righties. So what we're going to do is try to calculate the probability of the following number of lefties. Now, even though it doesn't explicitly say so, because the question, oh God, the question asks for the number of lefties, we will define success as being a lefty. Okay, so in other words, even if it doesn't say the words left-handed, being left-handed is a success, because that's what they're asking about. That means that that is how we will define success. And of course, that means that being right-handed is quote failure. So what we know is that there are 9 students in the class. Each one is a trial because they're either left-handed or they are not. They're all independent of each other. And the probability of success is the same for every one of them. So we have n equals 9, and pi, the probability of success, is 0.10. Okay, that sounds about right. In fact, you know what that reminds me? I do this in the classroom too. Any excuse for a poll. All right, let's do this. And usually what happens in a class of this size, all right, well, I'll tell you when we're done. Handedness, let's call it that. Are you left left-handed or right-handed, where I'm not giving you any other options, by the way. We're going to assume that it's either one or the other. All right. If you're ambidextrous, you're probably left-handed anyway. All right. Let's give this a shot, just for the fun of it. A lot of times in a class of this size, nobody is left. Oh, oh God, already two. That's a lot for a class of this size. Often when I do this in the classroom, I end up with none or maybe one. But I think 10% sounds about right. So, all right, yeah, I mean, you know how it is. You know, let's face it. Let's not kid ourselves. Everything in our society is built for righties. You know, you lefties know what I'm talking about. I'm not a lefty, but a lot of my family members are, so I know what they go through. But you might remember, yes, sadly enough, yes, although they do make left-handed stuff. They do make, for example, left-handed golf clubs, which that surprised me, why that would be necessary. They do make left-handed scissors. Sometimes in the classroom, they have left-handed desks, but there's very little effort really made to get around these problems. So I think that's one of the reasons why so many ambidextrous people are lefties, because they really just had to they were forced to use both hands since childhood. But on the other hand, sometimes it comes in handy. Like if you're a baseball player, being a switch hitter is a huge advantage. So, but anyway, okay. So anyway, enough of that. So what we're going to do now is calculate the following probabilities. So for A, we're looking for the probability x equals 0. So this is exactly the same question as this one, except with different numbers. So let's go through this. We'll do it two ways. We'll do it with the full-blown formula, and then we'll do it again with the calculators. Because, you know, we can't realistically assume that every single person has the calculator. And then n in this case, though, is 9. Okay, so for the first question, lowercase x is 0. Zero 0.10, the x is 0, and then we'll have 0.90. 9. Okay, so that's this one. All right, so x is 0, 9 is n. Okay, x is 0. Pi is 0.10. All right, so that's good. Now, let's check these out. Now, again, we have some quick, interesting results here. So, wow, 9 factorial is an enormous number. Whoa, 362, 880. It doesn't matter. You can see it cancels out anyway. And of course, I think I mentioned this once before. This actually isn't necessary. The number of ways of choosing, or actually, I think I'll do it this way. The number of combinations that can be created by choosing no objects from n objects is equal to 1. So in other words, the mere fact that x is 0 means that this piece is guaranteed to be equal to 1. And then, of course, we know that 0 to the 10th power is also equal to 1, because anytime you raise any number to the 0, it's equal to 1. So this piece is equal to 1, this piece is equal to 1. This is what we need to calculate with our calculators. So here's what we're going to have. The probability the hell is going on here? It's disobeying me. Wow, why is it doing that? I fixed it. I smacked it around. It's obeying me now. Okay, so we're gonna have 1 times 1, and then we just have to figure out the value of 0.9 raised to the 9th power, 0.3874 approximately. We'll just keep 4 decimals, 4 digits after the decimal, and that's our final result. Now, if you do happen to have the calculator, let's do that one. Here we go. So we have 9 trials, probability of 0.10, and x is 0. So if you throw these in, you should get the exact same result. All right, so go get that calculator. Pick binom PDF. And so trials is 9, p is 0.1, and x is 0. And you get, oh, I made a typo on mine. Hold on. 9. 3874. Beautiful. Then they're going to ask in part B for 2. Oh, we haven't seen 2 before. All right, wonderful. All right. So we just need to take this one and change it a little. Okay, so I'm going to doesn't seem to want to let me edit it. What the hell is going on? It's disobeying me again. Wow, that's weird. Oh, there it goes. It was asleep for a while there. I need to update this to show that lowercase x equals 2 rather than 0. Okay, so those are 2's. Now this is 2. This is pi raised to this x power. This is n minus x, so that becomes 7. Okay, be careful with that. All right, so 0.9 is raised out of the 7th power. These 2 exponents, by the way, have to add up to n, because one of them is x and the other is n minus x. In other words, if there's 2 successes, there have to be 7 failures. That's what these actually represent. There's 2 successes and 7 failures, therefore. All right. Now, this one is a little bit more challenging. These numbers aren't necessarily going to turn out to be easy, but they won't be that bad. All right, so go to your calculator. Now, this first term becomes now you can simplify this a little. Oh, how easy is that? The other possibility, which I completely forgot about, is that if you have the Texas Instruments calculator, I'll just throw this in here. Okay, you would put 9 and then you would hit math. Okay, so now obviously if you have the calculator, you can just solve for it directly. So there'd be no need to do this, but I just want you to know how this is done. So you would hit 9 math, and then you would choose probability, which is on the far right. And then you scroll down to number 4, which is factorial. Oh, sorry, that's not what we want. We want NCR, which is 3. And then you would hit, it shows in the screen as 9 rather, NCR. You would enter 3 and then enter, and you come up with 84. Oh, now does that, oh, not 3, 2, sorry, no wonder. The 3 is the menu item. It's 2 though that we're looking for. So it's actually 2. Let me try that again. 9 math, probability, NCR 2. It is in fact 36. Very good. All right, so that's just a side note. So that means that this probability will be, first we have 36. Now 0.10 squared is 0.01. Okay, now, and then 0.9 to the 7th power is 0.4783. So the product of those three numbers is approximately 0.1722. The key word there being approximately. You could get a slightly different number depending on how you've rounded your results. Okay, so that was x equals 2. 2 lefties out of 9. Okay, now for part C, oh, there we go. Once again, at least 1. Our old trick is here. Now, we may as well go through again. So at least 1, or greater than or equal to 1, can be written as 1 minus the probability x equals 0, which is 1 minus, and we already did this one, 3874. And so this is true regardless of how you approach this problem. 1 minus 0.38 so is 6126. Okay, 6126. Boy, that's convenient. Now, then we are asked to do the 3 moments. So the formulas are exactly the same, except remember here n is 9 and pi is 0.1. Good. Okay, so I just want to put those there again so you can see them while you're doing these problems. So I'm going to borrow the typing from up here. Oh, just because it speeds things up a little. I can't do this normally on a blackboard or a whiteboard. So I'm taking advantage of this capability. So it's 9 times 0.1. And that's so simple, it's equal to 0.9. So on average in this class, I should expect to get 9 left-handers. Okay, now what about the variance? Let's go borrow that formula. Here we go. So I'll have 9 times 0.1 times 0.9, and that's going to give me 0.81. And then finally, of course, we know what's coming next. The square root of the variance is the standard deviation. Let me grab that formula. Here we go. So we're going to substitute the new numbers. 9 times 0.1 times 0.9. The square root of all of that is exactly 0.90, as it turns out. Okay, and so you're done. So you've got 3 probabilities and the 3 moments. And that's it. That's all you'd ever actually be asked to do with a binomial distribution problem. Okay. So that's done. Now, what's coming next is a different kind of problem. Let's just quickly take a look at it before we have our break, just to see how it's different. All right. So, by the way, as usual, I'll be posting these solutions as soon as we're done so that you can look at it and go over it at home. If we don't quite finish it today, we'll finish it tomorrow. I'm not sure if we'll finish it today. If we do, it'll be very close, a close call. So this way you can study it all you want, and you can use this, as a template for your actual midterm. But look at this one now. On average, 3 customers enter the bank per hour. So is that a binomial problem? No. We have something happening, 3 customers walking in the door every hour. So because there's time involved, this is not binomial, this is Poisson. That's right. Now we're going to be looking at the Poisson distribution. All right, but first, it's after 11. We have to have our morning break before we collapse. So let's do that. And then when we get back, we'll work on this Poisson problem. And then you see, we're going to switch over to the normal distribution. Very good. All right. So I hope so far we're all keeping up. And again, like I said, you'll have copies of this to look at. And of course, tomorrow you can always ask more questions if you want to about what we did here. And then, of course, we'll go back to chapter 9. All right. So I'll see you all in a few minutes. All right, so here we are again. Now, I do want to mention one thing because I forgot from before. Let's go back and find Moodle. Where is Moodle? That's right. Well, oh, here it is. You know what I think we'll do here? Just because we can do this. Because you've got a lot of stuff coming up. You've got problem sets 6 and 7 still to be worked on and all this. Why don't we do this? How about just the midterm, not the chapter 6 and 7 problems, but you can have until Wednesday to hand in midterm number 1. Now that doesn't mean you should, procrastinate, but if you're not quite through with it, it's okay. I think I can afford to give you 2 more days. Like I said, since we're not going to be done until the 19th, but the rest of them, they really have to be done on time because, obviously the class ends on the 19th and I have to have the grades in, but you can have 2 more days if you need them. If you don't, that's fine. But just the mid. So in other words, try to make sure that you've got the chapter 6 and 7 problem sets done by tonight. And then if you need extra time, you can stretch it out until Wednesday for the first midterm, just in case you need it. All right. How does that sound? So the people who haven't started it yet are probably cheering right now, although I can't hear it because the microphones are muted. But yeah, I don't see why not. All right. So, but like I said, this is not a signal that you can be complacent because there's still a lot more that's coming due next week. All right, let's get back to this. Now, I did mention that this is now a Poisson problem because it involves time. So what are we being asked to do here? Well, first of all, let's go back and grab the formula from the slides for calculating probabilities with the Poisson distribution. Okay. It's not quite as complicated as the binomial formula, but here it is. And so, and I'll mention here in the answers here, since we are analyzing the number of events that occur per unit of time, we will use the Poisson distribution for this problem. Now, you don't have to write this into your own answers. This is just for your benefit. The probability formula technically it's the probability mass function for the Poisson distribution is, okay. And then also while we're at it, we may as well go back and grab the formulas for the moments because we're going to need them. There we are. Oh, that's so convenient. Okay, so we have these, and then the last one is an equation. So we can copy that separately. Okay, there we go. All right, so let's start at the beginning. Now, they're telling us that on average, 3 customers enter the bank per hour. So right off the bat, we know that lambda equals 3. Since 3 customers enter the bank on average per hour. So in part A, they're asking us to calculate the probability that no customers will enter the bank over the next hour. Okay. So they're saying the probability that x equals 0. Okay. Given that lambda equals 3. So let's plug in some numbers. So we're going to have e raised to the lambda power. 3 is raised to the 0 power, and then we have 0 factorial. Now, e raised to the third power, negative third power, that is. Make sure you can find that on your calculator. There's a button over there labeled ln. Directly above it, you can see it says e to the x. So make sure that you can actually calculate this Otherwise, you're going to have a problem. Okay, so that's approximately 0.0498. That's close enough. Now, 3 to the 0 power, of course, is 1. And 0 factorial is also 1. So our final answer is 0.0498. And it's that simple. Look how nice and easy that is. Now, if you're using the calculator's built-in functionality, let me go grab the instructions for the binomial. It's not much different, except, well, it's a little different. But it's on the same menu, and you're looking for a Poisson PDF. Okay. It's, there's no trials, so we're going to choose Poisson PDF. So if you go to that menu, it's down a ways. Actually, it's below the binomials. All right, so you just need to know lambda. And it actually says lambda in there. And directly below it, it says x value. So in our case, lambda is 3, x is 0, and then you'll pop in those numbers. And you'll come up with 0.0498. Not a surprise, because that's what we just got through using the actual formula, of course. It has to be the same. Oh, man, this one is so easy compared to binomial, isn't it? Yes. All right, part B, 1 customer. Okay, so I'm just going to borrow these. I'm going to basically recycle all my typing, but I'm changing x to 1. So here x equals 1. So in this formula, I only have to make a few small changes. 1, 1, and 1. So the e to the minus 0.03 minus third power will never change, but now this numerator is 3. So this new probability is 3 times that number, which is 0.1494, let's say, approximately 0.1494. Beautiful. Now with the calculator, you just change this x value to 1, and you should get the same thing. Let's just double check that. That's it, exactly. Beautiful. Now the next one's a little trickier, not really, because what you're being asked to do in part C is 2 or 3 customers. Ooh, all right, what is that all about? All right, so I'm just going to borrow these again. So 2 or 3, wait a minute. Okay, here we go. This is C. This is equal to x equals 2 plus x equals 3. So in other words, you have to calculate each one separately and then add them up. Think of these as mutually exclusive events. So what we're basically using here is the special version of the addition rule, or the simplified addition rule, when we have events that are in fact mutually exclusive, because you can't have both 2 and 3 customers coming in the door at the same time. So literally all you have to do is add these up. Okay, so in other words, you have to do this now for 2 and 3 and then combine them. All right, so this is now 2 2, and 2. So you have e to the minus third. Again, that hasn't changed, but now you have 9 and 2. And so this becomes 2241. Okay. Now we have to do the same thing for 3. And let's see what happens. So we change the x's to 3's. So this is now 27 over 6. Well, you know what? Just by ridiculous coincidence, we get the same number. Why is this happening? Because 9/2 and 27/6 are the same number. So the final probability is the sum of 2241 plus 2241, which is 4482. Wow. How do you like that? All right. Now with the calculator, we're going to do this twice where x equals 2, and again where x equals 3. And you'll discover that in both cases, you're getting the same thing. And then you're just adding them up. There really isn't any way of speeding this up besides doing them separately and adding them up. Okay. Now, again, you may have gotten a slightly different number depending on how you rounded your results. In fact, let me just double check something real fast here. I think on the calculator, it's rounding a little differently. It's rounding to 2240 actually. But again, that's just because it's all about rounding. So don't worry about these trivial differences. It's the same thing. So let's just be consistent here. The calculator is rounding this down to 2240. So therefore, let's just stick with that. Either answer is fine, 4480 or 4482. Okay? Beautiful. Now, what about the moments? They want us to do the expected number of customers, the variance, and the standard deviation. So we'll take these. So that's D, E, and F. Okay, here's D. Now remember, it's just equal to lambda. Oh my God, that couldn't be any easier. This is equal to lambda as well. And then for F, we're going to take the square root of 3. Wow, this is so easy. And of course, that's approximately equal to 1.732, let's say. That's close enough. All right, so that part is done. So I think you'll see that it's a little bit quicker than the binomial. And you've got two options. Now, obviously, you don't have to do this both ways. You can either use the formula or the calculator. You don't have to do both. But I recommend that you show your work even if you're using the calculator. So I know exactly what you did in case something goes wrong. Now these, the standard, no, by the way, you notice how it says the magic word standard normal. That implies, of course, don't forget about this, the standard normal distribution has a mean of 0 and a standard deviation of 1. That's the key to the whole thing. For any other normal random variable, they'd have to tell you the mean and the standard deviation. But here it's understood that there's 0 and 1. Okay, now this probability that z is greater than or equal to 0, what they're asking you to do is this. Okay, so that's what we're looking for. Now, if you look at the chart, you'll see that it has not exactly what we need. Hold on, let me go open up a normal table. So here's the 0. Remember, this is less than or equal to, though. That's telling me this probability. But because of the symmetry of the normal distribution, those are going to have the same value. Based on the table, probability z less than or equal to 0 equals 1/2. Therefore, the probability that we're actually interested in is equal to 1 minus that. 1 minus 0.5, 0.5. Okay. So that's why that's going to also equal 0.5. Okay. Now with a calculator, the following steps are needed. You go to second VARS, normal CDF, and then it's going to ask you for 4 things. Okay, what are those 4 things? Lower, upper, mean, and the standard deviation. Oh, wait. I thought I saw a chat. Sure, if you want to start midterm 2 sooner rather than later, that's not a problem at all. In fact, I think I'll do exactly that. In fact, let me just make a note of that to myself. Yep, absolutely. Yeah, if you think you're ready for it, that's fine with me. Okay. So anyway, so here we need sigma, mu and sigma. Oops, no, that's not what I wanted. Okay, so they're going to ask you for mu and they're going to ask you for sigma. Now in this case, the lower limit would be 0. The upper limit is infinity, which is E99. Recall, enter this as second comma 99, okay? And it'll show up as E99, and then you'll have 0 and 1. Now 0 and 1 are because this is the standard normal distribution. Okay, so I'm going to make a note of that here. And so if you put in all that, now the calculator will give you a slightly different answer because that E99 is not positive infinity. It's not quite that large. So you're going to get 0.499999, which you can round to 0.5. Okay? So that's how you would do this with the calculator. Well, that was part A. Oh, does it do that? Now, less than negative 1.88. Okay, well, we got a couple of options here. Now, since this is a less than or equal to probability, we can look this up directly in the negative table. Okay, so let's go get the negative table. We need negative 1.88. .0301, and that's it. That's literally all you have to do. Okay, so we know then that the probability Z is less than or equal to negative 1.88 is approximately 0.0301. And then with the calculator, very simple. Lower is now negative infinity. The negative on this calculator has that parentheses around it. Upper is negative 188. And of course, the mean and the standard deviation stay the same. Okay, so except for some potential rounding issues, because of course the table is somewhat rounded, you're going to get, let me try it on mine, negative second comma 99, negative 188. It's the same. Within 4 decimals of accuracy, it's the same. Oh man, we're flying through this, aren't we? Greater than negative 136. So this one clearly does not belong on the table, or is not found on the charts or tables. We have to make an adjustment. So if you look at the table, from the negative table, that is, we'll look this up, negative 1.36. And we will find that it is, in fact, at the intersection of negative 1.3 and 0.06, we find 0.869. Okay, and that's not exactly what we want, but it helps us. Okay. Therefore, what we need is just 1 minus that. Okay, so the actual answer that we're looking for is 9131. Okay, and so the shaded region, that's right here. All right, and then on the calculator, you'll have, you're just looking for just straight ahead, directly above. Let's see, what do we have here? Negative 1.36, positive, positive infinity. And yeah, we'll get the same thing. So I'm going to double check it on mine. From negative 1.36 to positive infinity, 91.31, after rounding it, of course. Beautiful. Oh, part B, no subtraction is needed because it's a less than or equal to probability. This is already on the table. Okay, you only need to subtract when it's greater than or equal to, or if it's in between. Okay, less than or equal to, you just do it directly from the table. Okay. All right. Because that's what the table is geared to show, less than or equal to, or what we call cumulative probabilities. And then finally, we have letter D. This is an in-betweener. So we don't need infinity, but we do need to calculate the difference between two different probabilities. So we've got the area between these 2 points. Okay. So we've already seen this before. We're going to actually calculate this as the probability that Z is less than or equal to negative 0.53 minus the probability that it's less than or equal to negative 1.87. So from the tables, the negative tables, negative 0.53 is, oh boy, where is it? Here it is. And you can't see the header, but that's the column for 0.03. There it is, yes. So that's 2981. And for negative 1.87, we have here and here. 0307. God, what's it doing there? All right, and the difference between those two is $26.74. All right, now what about the calculator? Well, the calculator is very simple. Looking at the range between two values. So what you're going to do is very simply put it between the lower would be the negative 1.87, the upper is the negative 0.53. Okay, the rest is the same. Okay, and so let's throw those in there. Negative 1.87, negative 0.53, 26.73. It's the same. Oh, it's almost the same. It's, again, the difference is due to rounding. The tables do a certain amount of rounding. So that's your final answer. All right, so we still have, now this is a normal problem, but not standard normal, because you can see the mean is not 0 and the standard deviation is not 1. And then we've got one more problem, which involves the normal approximation to the binomial. So what I'll do is I'll post the solutions that we have so far, as well as the second midterm, in case you want to get started right away. And then tomorrow we'll wrap up these last two problems, and then we'll revisit chapter 9 and the appendix. And if there's time, we'll start chapter 10. Okay, we have no time to waste. So, all right. So I guess I'll see you all tomorrow. Unless there's any last minute questions.
Have a good one, Professor.
All right. See you tomorrow. Oh, one more question. Oh, you're welcome. Okay.